Hello everyone, this side Dr. Isha Mehra, and today we are going to do few diffraction numericals and we are going to solve them together. So let's start. So the outline of my presentation is diffraction numericals. This will cover single slit diffraction, its formulas, and end slit diffraction. We also call it diffraction grating. So let's start with the problems, and in the meanwhile we are going to also discuss the formulas. So one of the numerical is a light of wavelength 6,000 angstrom falls normally on a slit of width 0.10 mm. We have to calculate total angular width of central maximum and also total linear width. As observed on a screen which is placed 1 meter away. So this is one of the very important questions even for competitive exams. Here we have to calculate total linear width as well as total angular width. So for diffraction pattern, single slit basically, what we knew is a source of light S is going to fall on a lens L, and this is going to get further collimated, and a slit is going to be kept here. This is single slit S. From here, the light is, few part of the light is going to go straight, and further it is going to get converge at lens L2. This one will be lens L1, and here it is going to get converge at some point O. The light is not diffracted here. From where the light will be diffracted? From the corners of the slit, like this. And the diffraction pattern, continuous diffraction pattern, we are going to observe here. So, because of this, we are going to get the patterns like this. The intensity is going to get decreased from either side of this point O. So in this case, what is this total linear width and total angular width? So in case of linear width, we can say if this is a slit and the light is going to get diffracted from here like this, so this will be the angular width. From one part of the angular width or the half part of the angular width will be theta. So the total angular width will be 2 theta. And if we talk about linear parts, we can say this will be R. If this is the focal length of the lens F, focal length of the lens L, which is given by F, then simply we can say 2R is equals to 2F lambda by A. So this is 2R is the total linear width. Total linear width. F here is given by 100 centimeter. It is given 1 meter. We are going to convert it because our width is also in millimeters, mm. So we are going to convert them to centimeters. So in this case, 2f is given, 2r is given by 2f lambda by a. F is 100. Lambda is the wavelength, which is given as 6,000 angstrom. So we are going to convert it to centimeters. So it will be 6,000 into 10 raised to the power minus 8 divided by A. And what is this A? This is 0.10 mm. So this will be 0.010 centimeters. So this will be 2R, which is given. If we are going to solve it, it will be 1.2 10 raised to the power minus 2 centimeters. And in terms of theta, it will be very simple. 2 theta will be 2 lambda by A. So, as we know that sine theta is lambda by A, so it's very simple. The theta is very small. So, T2 theta, that is the total angular width, will be given by 2 lambda by A. And if we are going to solve it, it will come out to be 1.2 into 10 raised to the power minus 2 radians. Is that clear? So total linear width will be 2r and total angular width will be 2 theta. So coming to the next question now. I hope this is clear to everyone. Now, the next question is, second question. Light of wavelength 5500 angstrom falls normally on a single slit of width 22 into 10 raised to the power minus 5 centimeters. Writing question is very important because when we are writing the question simultaneously, we are figuring out what is given to us, what parameters are given to us. So the slit width is 22 into 10 raised to the power minus 5 centimeter. We have to calculate angular position. Angular position simply means we have to calculate theta. But for what? We have to calculate angular position of first two minimas on either side of central maxima. For single slit, we are going to have the formula A sine theta equals to plus minus n lambda. So what we have to do? We have to find theta for n is equals to 1. And then we have to find theta for n is equals to 2. Theta is given by, that is sine theta, n lambda by A. Theta is very small. So from small angle approximation, we can write this as sine theta can be nearly equals to theta. So for n is equals to 1, it will be lambda by A. And if we are going to solve it, lambda is 5500 into 10 raised to the power minus 8. We have to take care about the units. It's very important because it's in angstrom. We have to convert it to centimeter because already our width is in centimeters. So it will be 22 into 10 raised to the power minus 5. So if we are going to calculate it, I'm calculating it. So it will come out to be 14 degree, around 14 degree. Similarly, theta for n is equals to 2. The formula will be changed. It will be 2 lambda by A. This almost twice of theta 1 So it will come out around 30 degree. So this formula A sine theta equals to plus minus n lambda is basically for single slit and it is a minima case. So we have to remember it. We don't have to get confused with end slit or grating. That part has different formulas. Now coming to the next question, question number 3. Calculate the angle at which first dark band and next bright band are formed in single slit diffraction having slit width, that is A here is 0.3 mm. So again, we have to calculate theta 1 and theta 2. So we have for single slit again A sine theta equals to n lambda. So theta 1 for n is equals to 1 will be sine inverse lambda by A. And sine theta 2 is equals to 2 lambda by A. So theta 2 will be sine inverse 2 lambda by A. So when we are going to calculate it, in that case, theta 1 will come out to be 0.112 degree and theta 2 will come out to be 0.168 degree. So it's very simple. For single slit experiment, the main formula is A sine theta equals to plus minus n lambda. Now we are going to do few grating numericals. So one of the grating numerical will be calculate angle between central image of a lamp and when it's diffracted, its first diffraction or diffracted image by a fabric has 160 threads per centimeter. The wavelength here is given as 6 into 10 raised to the power minus 5 centimeter. Now we have to find angle for grating. So for grating, the formula we have is A plus B sine theta equals to plus minus n lambda. This is for grating. For end slit, this is a case of maxima condition for maxima for end slit. For single slit, the condition for minima will be slightly changed. It is not going to have this factor of B. So it will be A sine theta equals to plus minus n lambda for single slit. Now we have to find the angle. Angle means we have to find simply sine theta. That will be given by n lambda upon A plus B. So n here we are taking as 1 because it's the first diffracted image. So the lambda will be 6 into 10 raised to the power minus 5 centimeters. A plus B is basically the grating element which is given by 1 upon n. That 2 in centimeters is given as 160 threads per centimeter. So in this case, it will be 6 into 10 raised to the power minus 5 upon 1/160 threads per centimeter. So in this case, if we are going to solve it, then we are going to have theta as 0.55 degree. We can also calculate it, convert it to minutes. So if we are going to convert it to minutes, it is going to be around 33 minutes. So we are going to do few more diffraction numericals, basically grating numericals, resolving power, dispersive power, and grating elements, etc. in our next presentation. So these are the few numericals we have done. Please practice them. These are very important for numerical point of view. In competitive exams, these are the references I have taken. It's also very important for engineering physics. I have taken this numericals from engineering physics from S.K. Gupta and the concept from Max Born and M.N. Wolf. Principle of optics. So this is the disclaimer. Thank you all.